Okay, so here we are again with another old exam question that I think dovetails really nicely with some of the material from the lecture. This is another one of the hard proofs, a proof which, I wouldn't want to ask students to do on an exam. I think it's a little too, it's too nitty gritty. There's too many details, but I still want students to have an idea of what's really going on and what's the point, or what's really happening in the proof. Okay, so as I've done on many other occasions, I have an old exam question, which walks students through a special case of really the exact same argument that makes up the proof. Okay, so that's what I want to go through now. And let's see here. I will share my screen. And here we have question 6 from 2019 fall exam 2. Here we go. And this question 6, I will get into the details here in just a minute. This question 6 is kind of a reference back to the argument that I eventually gave resolving the question of why the x to the m, right? There was this big mystery going, but this is section 4.3. Why, if the magic number is a root of the characteristic polynomial, why in that unfortunate coincidence does the multiplicity give you a power of x that you should multiply by all of the terms you would otherwise have guessed, your naive guess? What's the deal with that x to the m? Okay. All right, so we did talk about this in the lecture in section 5.2, and I gave you all this argument here. Hope y'all remember this page. This is on page 185 of the lecture notes. And now that I've done that, let me zoom in here, and let me point out what's going on here. I've given this lecture before, so I'm not going to repeat it, but the big idea is that we know how to solve this differential equation. Right? This is a case 1 situation where we've already gotten rid of the terms, the factors in the characteristic polynomial that have r as a root. Here, then, the r is not a root. And so this is a naive case, and we know how to solve these equations. We write down stuff like this. So we're good with that equation. So can I use that then, we ask, to solve to solve that equation, where you'll notice that my differential operator, right, does have r as a factor, right? So how do we deal if r is a factor, a root of multiplicity m? What do you do with that? Or said differently, how can I solve this differential equation? Well, the idea is to look at these two differential equations and first make the kind of smart alecky observation that, well, if I can solve the blue equation, and if I can figure out how to make these two things equal, then we're good. Right? So I need to, with the assumption that these numbers here are known, if I know what that solution is down there, can I figure out something? What would this thing here be? Let's assume we don't know the answer yet. That when I apply d minus r so many times to that thing, I get this polynomial down here that I kind of know works. Okay. All right. Okay, so let's look at the old exam question now, and let me zoom in a little bit more so we can see better. And you'll notice we kind of have that situation here. So here we have a differential. Oh, let me check the colors. Oh, I already. Okay, let me highlight this again. We have here a differential equation we know how to solve. Solution known in blue. And here that one is. We have a solution to this differential equation, right? And then the question is, how would I find a solution to this other differential equation? I want L of y equals g of x, but now L has this characteristic polynomial here. So let me rewrite L of y equals g of x like this. There it is, right? And so I want to know, what solves that equation. well, again, here's the green equation that I want to solve, and I want to know, what do I put there? Right. The difference being, of course, these factors of d minus r, and let's see here. Over back to here, these factors of d minus 2, but notice that 2 is r. That is the coefficient in the exponential. It's the magic number for this differential equation. Okay. All right. So same situation. And so just like we did back in this proof, I want to point out that when I say that what we really want to do is I want to make this happen, right? I want to find, what is the thing that when I apply the d minus r's to it, gives me the solution to the blue equation, right? That's what we're doing here. And that's how we're going to solve this question. We're going to ask, what is the thing here that when I do d minus r to it, I get the known solution to the other equation, right? So in other words, I want to do that. Okay, so let's again step back and think about the color coding. The color coding indicates the analogy between how to solve this problem and what was going on in this proof here, right? What we have in purple is our tricky kind of shortcut smart alecky move to try to use our knowledge of the blue solution to get our desired green solution. Same deal here. Okay. All right. So with that noted, let's actually do this. Let's try to figure out, well, what is then this thing that when I do a couple of d minus 2s to it, gives me this thing. And now don't forget what d minus r does here. Let me pick some other colors here. What does d minus r do? Well, d minus r, it kills powers of x, right? A d minus r is just going to reduce the power of x by 1. And then annoyingly, it messes with our constants, right? There's also this k out here. And ultimately, what we're going to see is this is the explanation for why I say that, we can solve, we can back solve for these c's. I claim that these constants are not going to be the same as these constants. And well, that's because of these factors of k here. And we're going to see that in action now, right? So on the basis of the fact that the power of x goes down by 1, we're going to speculate that, well, how many powers of x do I need in order to ensure that after 2 of them are killed, I get 6 left over? I probably need 8. Right? So that's the thinking there. But again, I don't know what this constant here is going to be because again, the other thing, the other annoying thing that these d minus 2s do, they keep spitting out constants, and so we'll have to solve for what that's going to be. Okay, so we speculate though that this thing I'm looking for, this y that I'm looking for, we speculate that it is a power of x, let's x to the 8th, e to the 2x, some constant. Our purple equation just becomes this, right? And now we just write down our rule a couple of times, right? What this does here, d minus r, again, every time you lose a power of x and you kick out a factor of k, namely whatever that exponent is. So you lose a power of x with each application, and then you kick out a factor of whatever that k is. So this kicks out that factor of 8, and doing it down here kicks out an extra factor of 7, which times the existing 8, of course, gives me 56. Yeah, so you do that, and then it's all over, really, because again, this was our guess solution there, and well, I know I need it to end up with 3 on the right. whatever A I have in there, I'm going to end up with 56 times it on the left. I need these two things to be equal. And so I can solve for A, thus giving me my solution. Oh, here we go. So this thing I was trying to solve for, there it is. Okay, so this is the process by which we, let's see, coming back up to here. This is the process by which we take the these D's down here. Go back to the blue. These D coefficients. The way we back solve for these C coefficients. That's the process that we just did. We started with our D was 3. That was the coefficient of the, well, the solution to the simpler differential equation, you know, the one where there's no unfortunate coincidence, that where we can just kind of write it down, easier to deal with. And that you can see in here, we have back solved for this A coefficient. That's the coefficient in the differential equation we actually wanted. Okay. All right. So again, the punchline to all of this is really just a way to help us motivate this original theorem. You know, what's the deal with the x to the m, right? Why x to the m? If there's a unfortunate coincidence of a magic number and root of the characteristic polynomial, well, that x to the m is to balance off these extra factors of d minus r that are allowing us to then have this circumstance where all I have to do is figure out what's the relationship between these constants. The x to the m sort of cancel the d minus r's. So, okay, that's what's going on with this question. Again, this was a hard old exam question, definitely challenging. But what I like about questions like this is very good for students to look back on and notice that this is a model. This is a hands-on guided sort of model to seeing what's going on in a much harder to write down, much harder to sort of, much more unwieldy proof from the notes. So I hope that'll be useful. Again, take a look at this solution here. Think about how what this solution does is give you an example of what's really going on down here. Okay. Hope y'all have a nice day.